The world is obsessively watching Flight 13, analyzing every static fire and flap test, but they are completely missing the real story unfolding behind the scenes. A recently leaked FCC authorization has just exposed SpaceX's true target for the end of the year, and honestly, it is terrifying. Buried deep inside the regulatory paperwork is a very specific, highly unusual phrase for an upcoming mission window that stretches all the way into December Orbital Return Demonstration. Let that sink in for a second. Not a suborbital hop, not a high-altitude test trajectory. Orbital return. Reaching orbit is fundamentally a matter of brute force. You build a big enough rocket, ignite enough engines, and push until gravity gives up. Returning from orbit, however, is a ruthless thermodynamic filter. If your thermal protection system fails by even 1%, or if your flight software miscalculates the entry angle by a fraction of a degree, your rocket instantly becomes a 100-ton meteor streaking across the sky. To understand the sheer scale of this incoming challenge, we have to look closely at the numbers. Suborbital reentry, which is the flight profile SpaceX has aggressively flown so far, hits the Earth's upper atmosphere at roughly 26,000 kilometers per hour. A true orbital return adds another 2,000 kilometers per hour to that exact equation. But wait, before Starship can even attempt to survive that orbital inferno, there is a massive, glaring hole in the timeline that no one is talking about. Many observers are rightfully asking, why has it been over 15 months since SpaceX caught a super heavy booster mid-air? Did they suddenly give up on the chopsticks? Or is there a fundamental physics problem forcing them to tear down and rebuild everything? Let's break it down. The mid-air catch of a returning 33-engine booster remains one of the most absurd, yet genuinely brilliant engineering feats of this century. But the absolute silence on catch attempts since that historic milestone has sparked a wildfire of rumors. Some say the FAA blocked it, citing public safety. Others claim the Chopsticks Tower is fundamentally flawed and structurally unstable. Both of those theories are completely wrong. The reality happening in South Texas is brutally simple. It all comes down to the laws of inertia and mass. SpaceX is currently shifting its entire operational focus to the massive V3 architecture. Booster V3 is significantly taller, holds vastly more liquid oxygen and methane propellant, and crucially, it lands heavier. If they attempt to catch a falling V3 booster using the old mechanical tolerances of the current launch tower, the sheer kinetic shockwave traveling through the steel would rip the mechanical arms right off the mount. That is exactly why you see massive, heavy-duty structural upgrades happening round the clock at Starbase, alongside the rapid construction of SLC-37 in Florida. They are overhauling the giant hydraulic shock absorbers hidden inside the carriage mechanism. Catching Super Heavy is not just about precision steering and software tracking. It is about physically absorbing hundreds of tons of dropping mass without collapsing the million-dollar infrastructure below it. They haven't stopped catching. They are simply upgrading the glove to catch a much heavier baseball. Now let's jump back to the orbital return of the upper stage. Why is an extra 2,000 kilometers per hour such a terrifying nightmare for the engineering team? Remember high school physics. Kinetic energy equals half the mass times velocity squared. That squared part is the ultimate killer in orbital mechanics. A 10% increase in atmospheric entry velocity does not mean a linear 10% increase in surface heat. It is an exponential spike. At orbital velocities, the supersonic bow shock compresses the atmosphere so violently that it creates a superheated, highly ionized plasma boundary layer around the belly of the ship. The thermal load attacking the black hexagonal silica tiles doesn't just get dramatically hotter, the plasma stream lingers longer across the hull. If the mechanical mounting pins holding those specific tiles aren't heavily upgraded to V3 specifications, the extreme vibration and intense thermal expansion will physically strip the rocket bare mid-flight, exposing the stainless steel skin to melting temperatures. Let's look at the retired space shuttle for a stark contrast. Its delicate thermal protection system was notoriously fragile, requiring thousands of hours of manual inspection. But worse, its orbital maneuvering engines relied entirely on highly toxic hypergolic fuels. Why? Because advanced cryogenic engines freeze solid in the harsh vacuum of space. And here lies SpaceX's greatest mechanical flex, the revolutionary Raptor 3 engine. An orbital return absolutely demands a flawless in-space engine relight. After floating in a minus 180 degrees Celsius void for 45 long minutes, traditional valves freeze, and external plumbing inevitably cracks under thermal stress. The sheer genius of Raptor 3 isn't just its record-breaking chamber pressure and thrust, it's the beautiful fact that they deleted all external plumbing. By smartly integrating fluid pathways and cooling channels directly into the primary 3D printed metal hardware, they naturally insulated the entire critical system. No exposed external pipes literally means no frozen valves. This minimalist, incredibly dense design is the exact reason SpaceX is highly confident they can consistently execute a reliable to-orbit burn. But while the upper stage ship battles orbital thermodynamics, the Super Heavy booster faces its own terrifying ordeal. Returning a heavily upgraded V3 booster requires threading a literal needle in the sky. As the 71-meter-tall stainless steel cylinder plummets tail first back toward Earth, it reaches supersonic speeds. Controlling that massive falling skyscraper relies heavily on the 4 grid fins mounted at the top. Because Booster V3 is substantially heavier and features a stretched aerodynamic profile, the dynamic pressure exerted on those titanium grid fins is immense. They act as air brakes and steering wheels simultaneously, fighting brutal crosswinds to guide the massive rocket toward a pinpoint location hovering just above the launch mount. Then comes the critical landing burn. Unlike the Falcon 9, which relies on a single center engine to touch down on mechanical legs, the Super Heavy executes a highly complex 3-engine suicide burn. This creates a lethal triangle of thrust that must balance hundreds of tons of steel perfectly in mid-air. There are no landing legs here. If the burn is off by a fraction of a second, the rocket smashes into the concrete. As it hovers, the giant Chopsticks Tower takes over the massive carriage, weighing hundreds of tons itself, slides up the rails of the tower using heavy-duty drawworks. Radar and optical telemetry physically lock onto the booster's load points, small steel pins protruding from the rocket's sides. The arms must swing shut in a matter of milliseconds to engage those pins exactly as the engines completely cut off. It is a violent, high-stakes mechanical ballet, which ultimately brings us back to the FCC authorization and the high stakes of Flight 14. Why the massive, unyielding rush? Why transition so rapidly to V3 and aggressively push for an orbital return demo before the end of this year? Because the NASA Artemis moon landing depends entirely on rapid, highly reliable orbital refueling. You simply cannot run a cost-effective space refueling depot if you throw away a massive, expensive tanker after every single delivery. But beyond the moon, there is an even bigger, far more lucrative endgame here. True orbital return unlocks the absurd payload capacity required to deploy the Starlink V3 AI network. We are talking about a space-based data infrastructure that requires lifting unprecedented amounts of mass to low Earth orbit on a weekly basis. Without a fully reusable Starship architecture capable of consistently returning from orbital velocities intact, the financial model for that mega constellation entirely crumbles into dust. Flight 14 is definitely not just another iteration in a test campaign. It is the final thermodynamic and mechanical exam for the V3 master plan. The exact moment Starship survives that 28,000 km/h plasma wall, and the booster engages those heavy-duty chopsticks, the rigid rules of spaceflight are permanently rewritten. The stainless steel hardware is ready. The orbital math checks out perfectly. Now it is just a matter of executing the brutal physics. Do you think SpaceX will successfully catch the heavier V3 booster and bring the orbital ship home in a single flawless mission? Let us know your thoughts and predictions in the comment section below.